In this video, we're going to look at constrained optimization. Most of the material can be found in the textbook by Dixit in chapters 3 and 4, and some of the second order conditions are found in chapter 8. Now I'm going to go into more detail and from a different perspective than Dixit, but these videos will enable you to follow that particular text. The other thing I should note is that there is some overlap with material that I've done previously, and where that's the case, you could probably just go through it a bit more rapidly than you might otherwise. So again, let's go and look at the problem of maximizing utility here, which is a function of Q1 and Q2 subject to this traditional budget constraint where I'm using the M for the income or budget. So at Q star, so here's the problem where we've diagrammatically presented it. So we have a budget line here, the straight line, Q1 and Q2 on the axes, and we know where this indifference curve U2 touches is tangent to the budget line. We have our optimum denoted by big Q star consisting of Q1 star, Q2 star. At that point, we find that the slope of the budget line, which is given by minus phi1 over phi2, where phi1, of course, is the marginal utility of 1, and phi2 is the marginal utility of 2, is equal to the slope of the budget line, which is simply minus p1 over p2. And we showed that the marginal rate of substitution is equal to the ratio of the marginal utilities, which is equal to the ratio of the prices. Now, suppose we take a particular function. We'll take this function f of x, this utility function, which is equal to x squared minus y squared plus xy plus 5x. The only difference is that we're going to now say that x and y are somehow related through this function h, which is a function of x and y, where x minus 2y is equal to 0, or if you like, x is equal to 2y, y is 1/2 x. We wish to find a maximum of this utility subject to this particular constraint. So the first order condition, we're using total differentials here, is that the derivative of the utility function, du, is equal to f of x dx plus, this should be f sub y rather than just y, dy. And we set that equal to 0. Now f of x, the partial of the function f with respect to x, is equal to the partial of the function with respect to y is equal to 0. But now, because of this constraint here, it's no longer sufficient condition for du to equal 0. So in other words, previously we'd seen that f sub x equal f sub y equals 0 was sufficient to make that du equal to 0, but that's no longer true. We need to consider the constraint itself. We can total differentiate the constraint. Dh is equal to the first partial derivative of h with respect to x times dx plus h subscript y dy equals 0. Assume that h subscript y, so that this component here is not equal to 0. And we multiply both sides by the first derivative, first partial with respect to y divided by the first partial of h with respect to y. So it's f of y divided by h of y. And we get dh equal to f of y, h of y, because we're multiplying through both sides. So this is 0 multiplied by that remains 0. And we get this times h of x dx. All right, we're just multiplying this by that. And then we multiply this by that. The h sub y's cancel, and we get f of y dy equals 0. So therefore, du is equal to f of x dx plus f of y dy equals 0. And we have that dh, we repeat this particular result here. All right, and then we subtract this equation here, the dH equals 0 equation, from the du equal 0 equation. So we subtract the second equation from the first, and that gives us this result, f of x minus this component times d of x, and then we notice that fy dy, those cancel and we get dx equals 0. So, assuming that dx is some small change and it's not equal to 0, we then have f sub x minus f sub y over h sub y times h sub x equal to 0, and we get f of x over h of x equals f of y over h of y. And we're just going to let that equal to minus lambda. So f of x over h of x equal f of y over h of y equal minus lambda. We've just chosen that. So then we get three equations. We get f of x plus lambda h of x equals 0, and f of y plus lambda h of y equals 0, and h as a function of x and y is equal to 0. And we solve these equations in the three unknowns for x star, y star, lambda star. Now, as shown by Dixit in chapter 2, we can reverse this process, and that gives us our Lagrangian. All right, we get this Lagrangian here, which is equal to the objective function, f as a function of x and y, plus lambda times the constraint h, x, y. So what we do is we set the Lagrangian with respect to x equal to 0, the partial of the Lagrangian with respect to y equal to 0, and then finally the partial of the Lagrangian with respect to lambda equals 0. So this then gives three equations the three equations up here that we had previously. So let's consider the above example that we were looking at. All right, this one up here. Where is it? Yeah, this one up here. And we're going to repeat that one right here in Lagrange form. So we get the objective function. That was we called it a utility function, plus lambda times x minus 2y. So we find the first derivatives with respect to the partial of L with respect to x. We get 2x plus y plus 5 plus lambda equals 0. With respect to y, it's minus 2y plus x minus 2 lambda equals 0. And the partial with respect to lambda returns the constraint again. So we can solve these three equations. And we do that, we find that x is equal to minus 2. So that'd be x star. X star is minus 2. Y is equal to minus 1. Lambda star is 0. And the objective function is minus 5. So the Lagrangian multiplier, or Lagrange multiplier, lambda, is simply giving us the change in the objective function from a marginal change in the constraint. All right, let me repeat that. The Lagrangian multiplier gives the change in the objective function from a marginal change in the constraint. And we know that to be a shadow price. It tells us how much utility will increase for a per unit increase in the budget or in income. And then we come back to the same thing that we had previously, that lambda is equal to the marginal utility of income, or perhaps more correctly, the marginal utility of budget. Now let's consider another example on the production side, where we have Q equals x times y. X and y are inputs. Q is the output. Subject to 2x plus y equals 6 is an ISO cost constraint. So in other words, we don't want to spend more than 6 units on purchasing x and y. And again, we form a Lagrangian like this with this lambda here. Notice I've got a plus here, and that minus 6 is there. So we take the first partial with respect to x, y plus 2 lambda equals 0. L sub y, so the partial with respect to y, we get x plus lambda equals 0. And if we look at those two, we've solved for lambda, we find minus y over 2. We solve this one, number 2, for lambda, and we find minus x. So we find that y equals 2x. We substitute that value in here. All right, this is the partial of the Lagrangian with respect to the Lagrange multiplier. And we get 2x plus 2 times 2x. And we get 6. But I see that that's a bit of an error. That should not be a 2 there. So let me just correct that a minute. Let's first erase that. So we get 2x is equal to 6. We get 4x, and x is 2/3. So these numbers all change. So we get 4x. 6 divided by 4 is 1.5, so 3 halves. We plug the 3 halves in here, and we get that y is 3. We plug the minus x, we get a lambda minus 3 halves, and we get that q then is equal to x times y is 9 halves. Or if we want 4.5 equals 4.5. All right. Now return to the Lagrangian for the two good consumer problem, and we just rewrite that Lagrangian here as follows. Okay, take the first derivative, the first partial derivative with respect to q1, we get lambda, or pardon me, we get marginal utility of 1 minus lambda price of 1. Same thing for the second one, marginal utility of 2 minus lambda p2, and we get the budget constraint back. From 1 and 2, we get that lambda is equal to the marginal utility of 1 over the price of 1 is equal to the marginal utility of 2 over the price of 2, which is equal to u1 over u2 equals the p1 over p2. So the ratio of the marginal utilities is equal to the ratio of the prices, and that's our marginal rate of substitution. Actually, it's the negative of the marginal rate of substitution because of the negative signs on these slopes. So solving 1, 2, and 3 simultaneously gives us these two equations, Q1 star, so in other words, this is the demand for Q1 as a function of P1, P2, and M, and Q2 star, the same thing as a function of P1, P2, and M. And this is known, or this is the Marshallian or the ordinary demand function. So these two are the Marshallian, or if you like, the ordinary demand functions. Now it also turns out, of course, that lambda itself is a function of P1, P2, and M, and lambda is the marginal utility of income, and it will change as the prices change and as the budget changes. Now suppose we have that utility is simply a Cobb-Douglas function with superscripts or raised to the power Q1 and Q2 both raised to the power 1. Then Q2 minus lambda P1 equals 0, Q1 minus lambda P2 equals 0, and again this constraint is 0. And when we solve these for Q1 and Q2, the same way we did here, we end up with these two Marshallian demand functions. All right, with this intermediate step where we solve using the first two equations here, this one and this one, we get that lambda is Q2 over P1 equals Q1 over P2. Solve that for Q2 and we get Q2 is a function or is equal to P1 over P2 times Q1. But that's not a demand function because you got Q1 here instead of P1, P2, and M. If we plug that value back in, here we do that here, and solve for Q1, we get that Q1 is M over 2P1, and Q2 is m over 2 P2. These are the Marshallian demand functions, but notice that there's a special thing here. Q1 is a function of its own price. In other words, if this price goes up, the amount of Q1 we buy goes down. And the same thing with regards to Q2. If P2 goes up, Q2 goes down. If M goes up, sometimes that pen jumps to M over 2 P2. So what I was saying is that notice that here we have M over 2P2 and M over 2P1. The demand functions are functions only of its own price and income, not the price of the other good. So the other good, the price of the other good has no impact, so there's no complementarity or substitution there. Now, as a student, you can show, and it's probably something you should do as an exercise, is show that if you have this utility function, which is a Cobb-Douglas function, that you're going to end up with this demand curve for Q1 and this one for Q2. And you'll notice that, again, the price of the alternative good does not enter the demand function. And this is a property of Cobb-Douglas utility functions. Now consider the second order conditions of constrained optimization. And we're only using one constraint here. In the next lecture, we'll go to multiple constraints, as the textbook does. So we want to maximize utility as a function of x1 and x2, subject to that phi of x1 and x2 is 0. The first order condition for a maximum and for a minimum is that the total derivative of du is set to 0 and the total derivative of d phi is equal to 0. The same thing for the minimum, and the second order condition says that the second derivative of the utility function must be declining, must be less than 0, and d phi must also be or remain 0. And for a minimum, the second total derivative of the utility function, the objective function, has to be greater than 0, has to be positive, and again, d phi, the constraint, has to be 0, the total derivative. So first order conditions then give us this traditional answer here. The only difference here is that we had P1 and P2 earlier. Now we've got a derivative of the constraint function, where this is the constraint function. So we have this result from the first two first order conditions, and this one from the third, where this is the derivative of the Lagrangian with respect to lambda. Now the second order conditions, x1 and x2 are not independent, so we let x1 depend on x2. Now things get a little complicated because we take the second total derivative of u, and we get that f1 and then the second total derivative of x1, because x1 depends on x2, so x1 is a function of x2. Then we get f, the second partial derivative with respect to x1, multiplied by dx1 squared. Same thing with second partial derivative with respect to x2 times dx2 squared. And then this term f12 multiplied by dx1 dx2. Now, the reason we have 2 there is because we'd normally have f21 dx2 dx1, but because of symmetry, f12 and f21 give the same result. And we also have to take the total derivative with regard to the constraint. We get the same looking function here. We get this d squared x1 dx squared, second partial derivative with respect to x2 dx2 squared, and again the same kind of idea here, except now we're talking about the constraint sets. To eliminate this term, we want to get rid of this term, dx1. So what we do is we take phi1 d squared u, all right, minus f1 d squared phi. So what we're doing is we're multiplying by the du squared 1 by phi 1 and the d phi squared by f1. So we get phi 1 f1 minus phi 1 f1 d squared x1 when we do that subtraction. And then the remaining terms are given in these square brackets. All right. And we've gotten rid of that particular term. So we're going to divide by phi 1, so the partial of phi with respect to x1, assuming that it's not 0. And we note that d squared phi is equal to 0. So with that in mind, we get this expression d squared u, where it's equal to f11 minus f1 over phi 1 times phi 11 times dx squared, f22 minus f1 over phi 1 phi 22 times dx2 squared, and 2 times f12 minus f1 over phi 1 times phi 12 dx1 dx2. Now notice, because we've got a dx1 squared here, dx2 squared here, and dx1 times dx2, we have a quadratic form. All right, so hence for d squared u greater than 0 or d squared u less than 0, the problem is to determine if the quadratic matrix is positive definite or negative definite. Remember, we talked about positive definite and negative definite matrices in the last or in several lectures ago. And we have a linear constraint, d phi, looking like that. And because it was the linearity caused this assumption, all right, that to hold. So for a minimum, we have that we create this, what is called a bordered Hessian. All right, this bordered Hessian consists of this border here, and some folks put the borders on the on this side and down below, but you get 0, phi 1, phi 2, phi 1, phi 2 there, and you get these results here from this quadratic form. All right, so this one here is this here. This part here is this part here. This part is just off of here, right there. And likewise, this here is this component. This component is this, and this one is down here. Okay, so you know where we put those things. For a minimum, that determinant of that bordered Hessian has to be less than 0. For a maximum, the principal minors bordered by the coefficient of the constraint equation alternate in sign, the first one being positive. So in other words, we'd reverse this particular sign if it were a maximum. So let's return to this Lagrangian here, and let's take the first partial derivatives with respect to x1, x2, and lambda. That gives us these results. And then let's take the second partial derivatives with respect to x1, x2, and then the cross derivatives. So we get that f1. So if we look at this one, f11 plus lambda phi 11, same thing for Lagrangian second derivative, partial derivative of the Lagrangian with respect to x2. We get f22 plus lambda phi 22, and then we get these results here. If we take first this one and take the derivative with respect of this particular function, we take it with respect to x2, we get f12 plus phi times, lambda times phi 12, And we do the same thing here. Now these two actually are the same because F12 is equal to F21 and Phi12 is equal to Phi21. So now what we're going to do is we're going to substitute this result, which we obtained above. Let's see if I can find that. Well, it's too far above, but you can go back on your own. We're going to substitute this result into these here and these. And we're going to get Lagrangian second derivative, partial derivative of the Lagrangian with respect to x1. We get f11 minus f1 over phi1 times phi11. Same thing for the second partial of the Lagrangian with respect to x2. And we get the same kind of results here. Then we get the bordered Hessian, which consists of these borders, and we then substitute these values here, 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 and here. In the case of three variables, it would look like this. All right, the bordered Hessian would look like this, and this is a symmetric matrix. So in other words, L13 is equal to L31. So the conditions for a minimum, the second order conditions for a minimum, are that the first principal minor, and notice that we have the total, we have a 3 by 3 matrix and we're taking the determinant of it, is less than 0. The full matrix, the determinant of the full matrix, is less than 0. And if we had more variables, they would all be less than 0. The conditions for maximum in this case are that determinant of the bordered Hessian is first greater than 0, then less than 0, and if we have more variables, more x's if you like, more inputs into production, or more quantities that are available, more goods that are available, they alternate in sign. So beginning with a greater than or equal, greater than 0 sign, then less than 0, then greater than 0, and so forth. If phi as a function of x1 through xn is equal to 0 is a linear constraint, then this Lij, so the second partial derivative of the Lagrangian with respect to xi, xj, can be replaced by Fij for all ij in the bordered Hessian. So in other words, we would get these L's would become F's. So for example, let's look at production, where production function is a function of x1, x2, and x3 subject to some cost, which is equal to the input price or the input price of x1, which we denote as R1, plus the input price of 2 multiplied by x2, and then input price of 3 multiplied by x3, plus this F, which is our fixed cost. And it just drops out. So the first order conditions are the ratios of the marginal products divided by the input prices, and they're all equal to each other. The second order condition is if we let x1 be a dependent variable, so that x1 is equal to this cost function, this cost constraint, if you like, minus the x1. So we take this x1 out, bring it to that side, the cost over here, and we get this function here. The second full differential of this function with respect to x1 is equal to 0. D squared q is equal to f11 dx1 squared, f22 dx2 squared, plus f33 dx3 squared, plus 2f12 dx dx2, dx1 dx2, plus 2 times f13 dx1 dx3, plus 2 times f23 dx2 dx3. And these 2's are there because the matrix is symmetric. So d squared q is a quadratic, And if we were to maximize that q, and we have the second total derivative of q less than 0, subject to this constraint, then we get this bordered Hessian. It has to be greater than 0, and the next one has to be less than 0. So they have to alternate in sign. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.